Morning students, now we are going to discuss about FPGA design flow. So it consists of design requirements, system simulation, either the program can be written in the form of system C, C++, MATLAB. This is going to be converted either in VHDL or Verilog. Then once the program is executed, the functional simulation is going to be established. Functional simulation is nothing but register transfer level. Once the simulations is obtained, the coding is converted into the synthesis level, that is nothing but gate level synthesis. The codings are converted into either in the form of AND OR gates or NAND gates or NOR gates. Okay, either it is an LUT based or it is in a MUX based. Okay, once if it is obtained, the components is placed in the respective configurable block in the FPGA. Either it may be in the Xilinx form or an Actalac form, or it may be in the Altera. Okay, once the components are placed, the interconnections are established. That is nothing but routing. Once the placement and routing is obtained, we are going to check the timing analysis. Timing analysis is nothing but if the input is given, when the output will be generated, what will be the delay between input and output. Everything is going to be tested by using the static time analysis. Once if this is obtained, it's going to be assembled in the FPGA chip, and the programming is nothing but FPGA programming is nothing but that is downloading the program into the kit. Once if the implemented into the kit, the next step is going to be testing. So we are going to be test the whole logic expression applying the test vectors. Here the synthesis is nothing but these are the steps obtained. The translation is nothing but we are going to convert the coding into the logic level. So the programs is going to be converted, the Verilog coding or VHDL coding is converted into the logic level. Okay, the translation is nothing but it's going to be converted. Then we are going to mapping is nothing but technological mapping. So what is technological mapping? It's going to be convert it is into the ordinary gates into NAND and NOR implementation, and the concept is optimization. Okay, the next one, it's going to be a decomposition. For example, we have in the configurable logic block only two input are present, three input are different. Depending upon the logic families, we are going to map the translated logic expression into the whatever we required. The next one, retiming. So the date retiming is nothing but if there is a large delay, the delay can be minimized by using the retiming concept. Once this is nothing but a technology mapping. Once the technology mapping is done, then the components is going to be placed appropriately into the configurable logic block. Then the routing is established. Routing is nothing but connections is obtained between the IO devices and the configurable logic block. So mapping, technology mapping, the schematic or HDL to physical logic units. So you look at this one here. This is 3 input AND gate, 2 input AND gate, 2 input OR gate, 1 flip-flop. The whole thing is going to be mapped into the LUT based. So the D flip-flop as it does, it is a register. Now the gates function can be obtained that can be implemented into the lookup table. Okay, so the compile functions into basic LUT based group. This is nothing but technology mapping. The next one, we look at it, how the mapping is established. There are possibilities. This is one LUT, this is another LUT, this is another LUT. how the logic gates are mapped into the LUT and it is going to be placed. Okay, now this is the flip-flop. So there are many configuration logic blocks present in the FPGA. Depending upon the gate, okay, two input gate or it is exclusive or three input NAND gate, it's going to be placed into the respective configurable logic block. Okay, the placement and routing. So the blue color boxes shows the configurable logic block. So each and every LUT are placed in the respective configurable logic block. Assign logic location on a particular device. That is called the placement. Once this is established, routing can be applied. Routing is nothing but iterative process to connect configurable logic block inputs, outputs, and IOC. It optimizes the critical path delay. Critical path delay is nothing but the largest delay between input and output. Okay, it can take hours or days for large and dense designs. So you look at it, how the connections are established between each and every configurable block. Okay, this is one block to the another block, one row to the another row. This is the same row, how the connections is established. Now, the iterative placement if timing not met. So depending upon the timing analysis, we have to do as many as iterations to obtain minimum the delay. Okay, now you look at there are so many configurable logic block slices. So each LUT to be placed in the configurable logic block. LUT 0, LUT 1, LUT 4, LUT 2, LUT 5, then LUT 3. Okay, so like that each and everything is going to be incorporated into the configurable logic block. This is nothing but it's a placement. Now routing. Once the LUTs are placed into the configurable logic block, if there are direct connections or in the long connections, everything can be established. This line is nothing but connections. So the same thing can be established into a vertex 2 architecture. The example is 64-bit adder. So how the program, this is the Verilla code. The Verilla code converted into a logic diagram. That logic diagram can be implemented into the chip. So this is the vertex 2 chip, that is XC Xilinx to vertex to 2000. So in the chip, how the program is going to be programmed. So the arrow which represents, so the configurable logic block and the routing, these lines is nothing but a switch matrix and the connections matrix is used to connect the configurable logic block with the input output through the SRAM technology or antifuse technology or EEPROM technologies. Thank you.